This is absolute value functions day 3. What we're going to do today is take an absolute value and change it into a piecewise, since we know that absolute values can be graphed as a piecewise. So a couple things. We saw this definition when we first started absolute value, that the absolute value can be written as a piecewise where we have, it always will be the positive version when your a is greater than or equal to 0, and it'll be the opposite of it when a is less than 0. This 0 here and here represents the x coordinate of the vertex. So some of the ones that we'll do won't be at 0, 0, they will be shifted left or right. But that number there is always going to be the x coordinate of the vertex. All right, so let's take a look at number 1. This x minus 3 in here, when I'm referring to just this portion, we're going to call that the argument. Stuff inside the absolute value. So when I go to write my piecewise, I have my f of x equals, I'm going to have my brace here. I'm going to have two different expressions and two different domains. So I have my x minus 3, and remember, a is greater than or equal to 0. Well, what has happened here? Our h value has moved 3 to the right, so our x coordinates moved 3 to the right. So now we have x is greater than or equal to 3. Okay, now we need the opposite of the argument, just like we have the opposite of a. So we have the opposite of x and the opposite of negative 3. But that's going to change what we put here, because now we have to have less than that number, so less than 3. Okay, so kind of to just visualize some other key points here, our vertex of this one, since we moved it 3 to the right, would be 3, 0. If you want to picture what this looks like, 1, 2, 3, 3, 0. Same slope as the parent function. What we just did is we described this part of the v, that's the part that's greater than 3 with the equation x minus 3. And then this line here, this ray, is the negative x plus 3. And that's what we're doing when it's less than 3. So we just took these two lines and wrote two different expressions for them defined on different domains. Okay? Now, sometimes they start moving things around in the argument, and it gets a little bit trickier. We still have our f of x here. We still want our first expression to be what the argument is, 7 minus x. We still want the second one to be the opposite, negative 7 plus x. But this part is going to be a little different because we had some transformations that happened. Okay, this is not the traditional way that we would write this. So we have had reflections, we've had some translations. So probably the easiest way to figure out what domain it goes with is to take the argument and set it greater than or equal to 0. So if we go back to the question before, let me show you how this would have worked. If we took x minus 3 and set it greater than or equal to 0, we'd add 3, and we end up with x is greater than or equal to 3, which is what we came up with. Okay, so let's try it on this one. We're going to either subtract 7 to this side or add x. Either way, if we subtract 7, we'd have negative x. It's greater than or equal to negative 7. Divide both sides by negative 1, which flips the sign. We'd have x is less than 7. So that's the domain that's going to correspond with this first one. And if that first one has a domain of x is less than or equal to 7, by default, the second one is going to have it greater than 7. Because it has to flip, has to be that other side. All right, what about if we throw a k value in there? Well, we have our f of x. We're going to, remember, keep the argument the same for our first line. So we'd have x minus 4. We'd still have the plus 2. But that's not simplified. So we do want to simplify that. Minus 4 and plus 2 is, of course, x minus 2. So we want to simplify. And then if we did the opposite of x, plus 4 plus 2. But that's not simplified, so we want to take the 4 and the 2 and add those together. So we'll get a 6. So our first one always matches the argument. Second one is always opposite of the argument. But notice when we did the opposite, we didn't take the opposite of the 2. You only take the opposite of what's inside the absolute value bars. All right, now let's figure out the domains for each of these. Just like up above when we took the argument and set it greater than or equal to 0, we're going to do the same thing here. We don't do anything with that 2. So x minus 4 greater than or equal to 0. Well, there's no funny business on this one, so that's just x is greater than or equal to 4. So that means that this one must be x is less than 4. And you can graph these by hand, graph them on your graphing calculator. We know that the vertex of this is going to be 4, 2. There wasn't any reflections or stretches or anything like that. But you can see it's going to look like a V, like this, except that our vertex is at 4, 2. And we're just describing each side. What the positive side would look like and what the negative side would look like. All right, last one. Same as all the rest. We want to keep this the same for our first line, but we want to do it simplified. So instead of me writing it here and then erasing it, I'm going to simplify over here. So we'd have 2 times x minus 3 plus 1, 2x minus 6 plus 1. So that's going to be 2x minus 5. That's my first line. Then we take the opposite of the argument, so the 2 does not become the opposite. Just the stuff inside the parentheses. The 1 does not become the opposite either. It stays a plus 1. Then we distribute negative 2x plus 6 plus 1. That gives us a negative 2x plus 7. Then we have to find when we're going to use each one of those. Well, again, this is not a tricky one. There's no switcheroos or reflections or anything in here. So we can tell that our vertex is 3, 1, which means it went to the right 3, so x is greater than or equal to 3, and x is less than 3. It's kind of a pattern each time describing the right and the left ray of the vertex. Absolute value, day 3.